Hello, my name is Duarte Almeida, and today I'm going to present our paper on high probability risk control under covariate shifts. So, machine learning models have been increasingly used in high-stakes applications, for example in fraud detection. In these systems, models assign scores to transactions and flag them as fraudulent if these scores surpass a given threshold lambda. And so, calibrating this threshold, as well as other decision-making parameters, is crucial to control predefined notions of risk, for example, the false positive rate, and distribution-free assertive quantification is an active area of research which provides the means to do so normally using a separate calibration set. However, standard methods assume that the calibration and test distributions are the same, but it is often the case that unlabeled data from new target distributions frequently arises, for example, when these systems are deployed to new settings. This begs the question of how we can use this older labeled data to perform calibration under the presence of a distribution shift, in particular a covariate shift. In this work, we address exactly this question, but we'll first do a quick overview on existing risk control techniques. So some methods, for example, conformal risk control, are able to guarantee risk control in expectation across all possible calibration sets. But what we can do instead is high probability risk control. So here we ensure that a given calibration set provides risk control with confidence at least 1 minus delta for some delta between 0 and 1. And learn and test is a flexible tool to achieve this property. So given a candidate set of parameters lambda, it identifies a subset lambda hat such that simultaneously for all the parameters within that subset, the risk is controlled with very high probability. Moreover, within this subset, we can perform a specific choice small lambda hats by minimizing other risks. For example, we could minimize the false negative rate in the fraud detection use case. In essence, learn and test frames risk control as an hypothesis testing problem. So to check if lambda controls the risk with confidence 1 minus delta, we test the null hypothesis that the risk is not controlled, and if we can reject it at a significance level of delta, then we can assert risk control with probability at least 1 minus delta. Usually this involves a computation of a p-value over the calibration set and rejecting the null hypothesis if it lies below delta. Examples of p-values include the Cloper-Pearson p-value, which is particularly suitable for 0-1 losses, because in that case we can always specify the distribution of the empirical risk R hat. But it is important to note that p-values assume that the empirical risk is unbiased with respect to the target risk, which does not happen in general unless the calibration and test distributions coincide. To obtain the risk controlling subset, we have to ensure that the probability of a single false rejection within the entire set is at most delta, so just testing individually each hypothesis does not suffice. And a popular method that can achieve this property is the so-called fixed sequence testing. So here the hypotheses are tested sequentially until the first known rejection occurs, and all the parameters which were considered up until that point will form the risk controlling subset. To apply learn and test, we'd have to ensure that the source and target distributions are the same, but under the covariate shift assumption, even if the feature distribution changes, the feature conditional level distribution remains the same. So, as a consequence of that fact, we can link the two distributions through the importance weight function, which depends solely on the features x, and it can be completely estimated just using unlabeled source and target data. Existing approaches to deal with covariate shift for high probability risk control, such as the one proposed by Park et al., use rejection sampling prior to the application of risk controlling techniques to effectively align both distributions. In practice, these methods construct a new calibration set by resampling each point with probability equal to the corresponding importance weight over some estimate p of the maximum importance weight. But we can see if b is very high, we can throw away a lot of data, and consequently our p-values can become very weak and our risk controlling procedure can become very conservative. This naturally begs the question if we can still account for covariate shift while retaining the full calibration set. So to solve this problem, our methods proposes weighting the losses prior to the computation of p-values, and in subsequent slides we'll show how to do it for two different classes of risks, first for joint risks and then for conditional risks. If the risks are defined over the joint feature and label distribution, like the miscoverage, then weighting the losses over the calibration set by the corresponding importance weights will make them unbiased with respect to the target risk. And in particular, this means that we can use this sample of weighted losses to compute p-values, and we'll still retain the same formal guarantees as before. It is important to note that while this method retains all the source data, the distribution of the weighted losses can be very challenging to handle. In particular, this weighting process can break some pre-existing 0-1 structure or can broaden the range of possible weighted loss values. But recent advances in testing by batting have provided very variance adaptive p-values, which work very nicely in practice, such as the p-value proposed by Wadby Smith and Hamdes. And another key detail is that p-values assume that the losses are between 0 and 1, which may not be true after this weighting process, but luckily we can just rescale both the losses and the risk threshold, which we can do once we have an estimate of the maximum importance weight B. For conditional risks, we just condition the expectation on some non-zero probability event, as is the case of the false positive rate. And fortunately, we can always recast any conditional risk as a joint risk for the purposes of hypothesis testing. So in particular, by doing some algebraic manipulations using Bayes' theorem, we can always recast the original risk controlling problem as controlling a new surrogate risk R prime, which is itself defined over the joint feature and label distribution. We'll now detail the experimental setup used to evaluate this methodology. We consider two tasks. On the first, we aim to minimize the false negative rate of a fraud detection model while keeping the false positive rate below 0.05 with 0.95 confidence. And we also consider a task of minimizing the average set size of an image set predictor while controlling the miscoverage below 10% with confidence 0.95 as well. For the first task, we consider a synthetic dataset generated by resampling the bank account fraud dataset according to the credit risk score of the clients that made the transactions. In particular, we construct 3 domains made up of clients with different credit risk score levels, namely low, medium, and high. We consider each one of these domains as targets in turn, while the remaining ones form the source domain. And also by construction, it is the case that covariate shift assumption is guaranteed to hold. For the second task, we'll use the domainnet dataset, which is composed of 6 domains of images of different natures, to simulate a scenario where a model is trained on broad data but deployed on a specific subpopulation. We consider each domain as target in turn, and all the domains are pooled to form the source domain. Also, this time around, the covariate shift assumption is not guaranteed to hold. Although we assume that importance weights are accurate and known, they still have to be estimated, of course, and for that purpose, we employ the kernel min-matching algorithm, and we just consider the sample maximum of the importance weights as an estimate of B, the maximum importance weight. We'll now analyze some results for the first task. We compare our method of using importance weights, which we call LTT-IW, to the usage of using rejection sampling, LTT-RS, as well as to the plain original learning and test framework. Here we show the 0.95 quantiles obtained over 1,000 iterations of risk control using calibration sets of varying size n, which we show in the x-axis, just to get a sense of data efficiency. We also show the 0.05 risk threshold in a red dashed line to assert whether or not the risk is being controlled. Results show that both variants are able to control the FPR in nearly all cases, with the exception being for the domain medium, where we have this small residual risk gap which can be attributed to errors in the estimation of the importance weight function. We do a similar analysis for the false negative rate, but consider the mean false negative rate obtained over the 1000 iterations, and results show that our method is less conservative than the rejection sampling baseline because it is able to achieve lower FNR values on average. Now, when we analyze the miscoverage control for the domain net case, we note that the risk is only being controlled either when real or quick draw are taken as target domains, which of course indicates a failure of the covariate shift assumption. Nevertheless, we note that using some kind of covariate shift adaptation can effectively close the risk gap. And also analyzing the average set size, which is the unconstrained metric, we again see that our method yields less conservative solutions, which in this case is not always desirable because it can come at the cost of increased risk violations related to the miscoverage. So we note that when the covariate shift assumption is not guaranteed to hold, this trade-off always warrants some caution. In this work, we have shown that using importance weighted losses can be an effective tool to deal with covariate shift when doing risk control with high probability, and future research could focus on relaxing some of the underlying assumptions. For example, we could eliminate the need to specify the maximum importance weight B. We could also take into account errors that arise when estimating the importance weight function, and we also note that it could be the case that using rejection sampling could be the better method, so of course coming up with an automatic selection procedure between the two could also be a very interesting future research avenue. Thank you very much for your attention.